Thank you. It is a pleasure to be here. I didn't know that I knew so many people here, and I've taught some of them. Jamie Schofield in chemistry I taught when I was at MIT, and then I also taught Andrew when he was at Illinois. And I used to have office hours at weird hours like 2 in the morning, which Andrew came to. Okay, so he's a very conscientious person. Okay, so I'm going to try to convince you about one thing, that, well, this will definitely be something you will be convinced of. Whether or not it's correct or not is a different question. Okay, I'll definitely convince you that my current thinking is that the best explanation, okay, the best explanation for the what's going on in the normal state of superconductors is that they have an extra dimension. Okay, and the key people who have been involved in this project are Kurtzangapong Limtragul, and a student of mine, and a math colleague, Gabriele Lanave. Okay, so let's just ask, given that I have a title, a question for my title, one is struck by this quote, is Hinchcliffe's rule true? So Hinchcliffe has asserted that whenever the title of a paper is a question with a yes or no answer, the answer is always no. This paper demonstrates that Hinchcliffe's assertion is false, but only if it is true. Okay. Okay, so I thought I would start with a joke, warm you up, because I was trying to figure out how was I going to present this talk, and I thought I would give a Blackboard talk, and I was told only one person has done that. And so, not knowing if I could follow in that person's footsteps, I decided to give a slide presentation. The topic is somewhat technical, but I've tried to introduce it in the least technical way possible. So with that proviso, let me just start with a series of equations. Okay, what would be the signature of extra dimensions? Okay, so here would be the signature of extra dimensions. Okay, all of you know these equations. These are Maxwell's equations. Okay, now these equations are very complicated, and we've all had to memorize them. But these equations are really more complicated than they need to. Okay, so far nothing about extra dimensions yet. Okay, so because we know that the E field and the B field really come from our manifestations of some other potential, okay, the vector field. And once we know everything about this, we can describe all of electricity and magnetism. So what God really said was, let there be F, okay? And F, written in differential form, is just dA. And once you know F, you can write down the electric field, and you can write down the B field. And they're just various components of F, the field strength, or in various languages it might be called the curvature. Okay, so I'm building up very slowly because I need you to understand F throughout this whole talk. Okay, so, and a Maxwell equation in terms of F is now very simple. dF equals J. Okay, that very simple equation that we can all remember. And I want you to remember this equation. Okay, now given that E and B can all be formulated in terms of A, it tells you that there's a redundancy in electricity and magnetism. If there's a redundancy, there's a symmetry, and this will manifest itself as a gauge symmetry. Okay, so that gauge symmetry is that all of electricity and magnetism is invariant under this transformation. A going to A plus partial lambda, and lambda is a dimension, it has no units, and which means that A has to have dimension 1. It has 1 unit of momentum, and hence A is dimension 1. Okay. And the field strength is invariant under this transformation. Okay, so now anytime there's this underlying symmetry, it has to be coupled to a conserved quantity. The vector field is coupled to the current, and one can see that by formulating a Lagrangian formulation of electricity and magnetism. You simply vary A. The key thing is you get all of the equations of electricity and magnetism. The Lagrangian that you would take is simply this right here. It's this action, F squared, and J and A always appear in this linear form. So this is the source for the current. Okay. Now, if you just apply this gauge transformation to this action, this is invariant. This term will transform like this. You'll have everything here in S plus this extra term. Now, the action has to be invariant under this transformation. So for it to be invariant, you have to demand that this term somehow vanishes. But you make that term vanish in a fundamental way. Just integrate this term by parts, flip the derivatives onto J, and then you end up with that equation, which is the current conservation equation. Okay, so gauge invariance, and note, the form of this transformation, this being a linear derivative with respect to this dimensionless function, and this being a single derivative of J, those two things are absolutely related. So gauge invariance and current conservation are flip sides of the same coin. Okay, so just to summarize the sort of principles I need to give this talk: gauge invariance, current conservation, A having dimension 1. Okay, now this also fixes the dimension of the current. Because remember now, if this has dimension 1, and the things which appear in the action all have no dimensions at all, then it has to be the case that this quantity has no dimension, which means J has to have dimension d minus 1. So all of us learned when we took field theory that conserved quantities have fixed dimensions. And this cannot change even when you do renormalization. So you start off life with some action that is U1 invariant. At the end of the day, when you've done all the renormalization, you can change the dimension of A. The fields can acquire anomalous dimensions, but nothing that is coupled to a conserved quantity can acquire an anomalous dimension. Okay, so that's really the first thing I wanted to establish. Okay, now what if, magically, what if, imagine a world in which the dimension of A was not equal to 1, but nonetheless the current is conserved. Now everything I've told you up to now would say that this is impossible. But what if this were true? If this were true, this would imply that there were extra dimensions. Okay, and that's really the message of my talk. So I want to introduce a playground in which this might happen, explain how this happens, and then propose an experiment to test if in fact this is true. Now, it should not be obvious to you yet that this implies that there are extra dimensions, but it will be in about 20 minutes. Okay, any questions yet? Okay, all of I've told you, you can, it's just standard, you can read it in Peskin and Schroeder or in your other book. Okay. Okay, now where might this be seen? Okay, so there are these materials which have been perplexing the physics community, and it's now really the physics community. This problem has been so hard that the condensed matter theorists have allowed the string theorists to work on these problems. And it's because this problem embodies all the things which are hard about physics. This is a problem at strong coupling. So we have this material which looks very pretty. The electrons are confined to move in these planes, and the interactions are very strong. It's very much unlike mercury or any elemental superconductor because those materials start out their lives as very well-defined metals in which you have well-defined quasi-particles, and none of the physics that I'm talking about would at all be relevant. Okay, so now the key thing about strong interactions is that an independent particle picture does not work. So there's some collective phenomenon coming about. And when you are trying to understand collective phenomena, it helps to know what is the organizing principle. Because it's not based on your intuition, based on what the individual particles are doing. Okay, so we have high temperature superconductors. They start out their lives in what is called a strange metal, and as you cool them down, they superconduct. And the problem is, how does this happen? Now, we don't know how this happens because we don't know what is going on with the strange metal. We don't understand how to write down a theory for these basic excitations that exhibit all of these exceptions to the standard theory of metals. Okay, so what is this strange metal? What are its properties? Well, let me first start off by telling you what normal metals do. Okay, so a normal metal is just described by the Drude formula. Electrons bounce off of the atoms, and in an electric field, the rate of change of the momentum is governed by this linear term over here with the momentum, with some relaxation rate here in the denominator. So this is the standard Maxwell part, and this is the key part right here. This relaxes the momentum. If you didn't have this in this simple kind of model, for example, this is now what the conductivity looks like. If you look at the real part of this conductivity, in the limit that tau goes to 0, this conductivity goes off to infinity, so you aren't really describing a metal. You also aren't describing a superconductor. It's really just a perfect metal. Okay, so this is what what we think about electrons bouncing off of impurities that gives rise to some relaxation time, some finite rate of scattering, and everything else is the interactions between the electrons is sort of irrelevant. Okay, now here are properties of the standard theory of metals. The resistivity goes to 0 as the second power of the temperature. There's the Wiedemann-Franz law. The ratio of the thermal conductivity to the actual conductivity is a constant. It's not dependent on temperature. And the real part of the conductivity scales as 1 over omega squared. Now, the important thing is not these functional forms. One of the key things here is that this number and that number are the same. So the temperature dependence and the frequency dependence fall off or scale with the same exponent. That is one of the key things about the standard theory of metals. Okay. Now, here's what a strange metal looks like. Remember, it was T squared. Here, the resistivity over a very wide range scales as a linear function of temperature. If you look at the optical conductivity, this scales as omega to the minus 2/3. And remember, in the standard theory, this power and this were the same. Here they're fundamentally different. And if you look at the this thing that's supposed to be a constant, this ratio, it's now not equal to a number, it's proportional to temperature. So there's a violation of Wiedemann-Franz, T-linear resistivity, and the frequency dependence of the conductivity is this weird algebraic power. Okay, now if you look at the theories of the cuprates over the theories of the strange metal, if you see me look at this ratio, this number is basically infinity, and it's because there are an exponentially large number of these such theories and basically 0 of the strange metal. Okay, now why is this problem hard? Well, it's something I've alluded to. It's hard because if you try to understand all these power laws, generally critical phenomena gives rise to power laws. So let's just assume that there's some sort of critical phenomena going on. And when you do that, you introduce some sort of scaling. Let's just look at the simplest picture, one parameter scaling. So we scale time the same way we scale length, just length to some power. You break the system up into these correlation volumes. And what you find is, as no surprise, this quantity here has the same exponent here, just the negative. But in the cuprates, this you want to be 1, and this you want to be minus 2/3. Well, since they're governed by the same exponents, essentially, it's impossible for these to give you two fundamentally different numbers. And that's why the problem is hard. Because the first thing that you would try, which works very well for almost everything else in nature, does not work. Okay, so what we need is some new length scale, or some new degree of freedom. Okay, now, along came a pure string theorist and someone who's trained in gravity but has a background in strings and is working on condensed matter. They propose that they can explain all of these properties of the cuprates if they make one assumption. And that assumption is that the current no longer has dimension 1, and the vector potential no longer has dimension, the current no longer has dimension d minus 1, but it has this funky behavior, and A no longer has dimension 1, it has dimension 1 minus phi, and phi is minus 2/3. Okay, so this means that they are saying what is strange about the strange metal is that the current and the associated vector potential, which sources the current, have anomalous dimensions. I spent the first 7 minutes of the talk showing you that that's not consistent with standard electricity and magnetism. So if this claim is correct, there's something fundamental that we have to sort of change in our thinking about electricity and magnetism. Okay, now never mind about all of these numbers here. The key thing is that the vector potential, which is sourcing this, has a dimension which is now 5/3, which is significantly different from 1. Okay. Now, I had written a paper, when this paper came out, I'd written a paper 10 years earlier saying that the reason why the problem is really hard is that even if you were to introduce an anomalous dimension, you could not explain these properties. But they figured out a way, well, they just did some scaling and they said, okay, so we can get everything. Okay. Okay, now recall, in standard electricity and magnetism, A is 1, and this has dimension d minus 1. Okay, now in the strange metal, this is the behavior. Now how is this possible? That's really the subject of my talk. Okay, now there's a hint as to what might be going on. Before I get to that hint, let me just tell you something. The reason why this explanation is problematic is that if A doesn't equal 1, the dimensions of A don't equal 1, then the standard gauge transformation that we know about, since this is dimensionless, this can't possibly be true. Because this tells you that A has to have the dimension of the momentum. So this can no longer be true. So if the strange metal is strange, we have to come up with a new gauge principle. And so what is that new gauge principle? Now here's a hint as to what might be going on. The current conservation equation is this. Okay, now what if I can find a quantity that I can insert between this derivative and J that in fact commutes with this derivative? If I can do that, this will effect, I can pull that out, but I can also use it to redefine what J is. Which means if I can come up with some quantity, some operator, which is non-trivial, so clearly a constant will work, but I wouldn't be giving you a colloquium if I was talking about a constant, okay? Okay, so, right. So clearly, if I can solve this equation, or if this has a non-trivial solution, I can use this quantity to redefine what the current is, and the new current now would have this dimension. Okay? If that's possible. Now, this is not really sophisticated, because what I'm saying is that anyone could have done this. What this would say is that that would redefine what A was, And the E and the B field would be the ones associated with this funky A that's giving rise to this funky current. And standard electricity and magnetism then admits this ambiguity. I mean, you can always add the curl of anything to the current. That's not the ambiguity I'm talking about. I'm saying that there is a multiplicative factor, an operator, that if in fact one can find that commutes with the derivative, then the current can have any arbitrary dimension. Okay. Well, the question is, how do you find y hat? Okay, does anyone know how to find y hat? Does anyone have a guess as to what y hat is? Because if you do, I can just end the talk right here. Young Beck, do you know what y hat is? Okay, I should mention that Young Beck and I were in Aspen when Sean Hartnell presented this, and we both went crazy. I was much more vociferous in my criticism because I thought the idea was absolutely wrong. But then I went back, I started thinking, I've been obsessed with this ever since, that was essentially the last time I saw you. Okay, so does a non-trivial solution exist? Okay, now, perhaps the answer lies by appealing to string theory. Okay, this is such a sufficiently complicated problem that the only thing that could possibly solve it is string theory. Okay, so let's, and in fact, you know, David Foster Wallace is from Champaign, Urbana. At least he was from there, okay? Okay, so does this, how would this possibly solve the problem? So we have this strongly correlated system, and with a strongly correlated system, to tell any story about it, you need to be able to construct the low energy limit. Okay, now how do you go from the UV complete theory to the low energy limit? Well, one of the things that's very popular in our field is to use what's called the 1 over ego approximation. Okay, so if in fact, so this is a problem in which the coupling constant is large, so you can't really do an expansion in it. But if your ego is sufficiently large, this coupling constant goes to 0. Okay, and then you just write down the answer. Okay, and then the power, the success of your answer is governed by the strength of your personality. Okay, so let's not do that. I live in the Midwest. I can't get away with that, so I have to really go and compute something. So how you would really do this is you would write down the beta function. You would say, I want to think about this quantum field theory as a bunch of slices, all of them living at different energies. And if I know this coupling constant is running, I can then ask the question, what is this describing in the low energy regime? Now this procedure is local in energy, and hence it has to be local in space, and hence one might think you could geometrize this whole thing. Well, that is the essential thinking behind Maldasena's brilliant gauge gravity duality construction in 1997. That the quantum theory lives at the boundary with its degrees of freedom, but this is really just a sort of glimpse into a much bigger theory which is living in an extra dimension, and this direction is the running of the RG coupling constant. So what comes out of Maldasena's conjecture is that there are certain strongly coupled quantum theories which have gravity duals, and this field is called holography. In the original paper by Maldasena, the specific example he worked out was for a space-time which is asymptotically anti de Sitter, and this is dual to a boundary theory which describes the structure of nucleons. There's a particular formulation of Yang-Mills theory, and whose details I will not go into right now, but the important thing is that there is quite a bit of evidence for this particular duality. Okay, and because of this, many of us are interested in, are there other examples in which boundaries of this space-time, which is asymptotically anti-de Sitter, really corresponds to a dual of a gravity theory which is weakly interacting. And that's when I became interested in this problem. Okay, so here's the claim. The claim is what motivated Hartnell and Karsh to propose that, in fact, there is an anomalous dimension, is that if this is the boundary of the system at y equals 0, and in here where the black hole sits, this is y equals 1, so this is the radial direction. Their claim is the following. If you write down a series of a theory in the bulk of the system, which doesn't look like standard electricity and magnetism, so it's a theory of electricity and magnetism in which the coordinate here is sort of dilating everything, so it's called a dilaton field, and F is just dA, and the crucial part is just the electricity and magnetism part. If you simply write down this theory, the claim is that this produces, at the boundary, a quantum theory in which A doesn't have dimension 1. And okay. So let's start our analysis by looking at this action. Okay. Now, so this action just has the standard volume factor, but it also has this extra integration over y. And what I want to do is do what I did at the very beginning, simply take the equations of motion of this. Okay, so the equations of motion just look like this, a very simple equation. I don't have the current here, so this side is just 0. Okay. Now, what's interesting about this equation, because d squared a is equal to 0, along any slice through this system here, this gauge transformation is true. Nothing changes in the bulk of this system. But if you set y equals 0, you can't really figure out what's going on at the boundary. So this question is, what happens at the boundary? Okay, now this is a problem that I just want to take a step back and reflect on a theorem proven by two analysts in 2006. So this theorem was not available when the original ADS-CFT conjecture was written down. Now the whole thing in holography, you have a larger dimensional system and you're asking what's its behavior in a smaller dimensional space. Okay, so some mathematicians were interested in the properties of differential equations that look like this. This is just a second order differential equation. G is the function. X and y are coordinates. Here I have x and y, and x can be any number of coordinates. what they're interested in is if you look at this equation, what form does this equation take on if you take the limit as you approach this boundary? Okay? What happens if you eliminate this coordinate and you're particularly interested in the limit of this quantity right here as you approach here? Well, what they found is that this is just the fractional Laplacian raised to a certain, the Laplacian raised to a power, and that power is not 1. The power can be any fraction depending on what number you put here. So gamma is 1 minus a over 2. Okay, so let me, right, so, yeah, this is just the fractional Laplacian. Okay, does everyone have a piece of paper? Okay, let me illustrate this point. But you can also do it by just taking out a piece of paper. Okay, now let's say I construct a quantum theory on this sheet of paper. Okay, and I do that with the standard sorts of things we build quantum field theory from. Operators which are purely local. So, integer derivatives. And that has to do with translations, and there might be some interactions. So from that I can move anywhere in the sheet of paper. Okay, now what if I bend this piece of paper this way? Okay, so I've sort of added an extra dimension. Okay? Okay, if I've added this extra dimension, I can still have a theory which lives in all of these dimensions and allows me to go from here, down here, into here. But what if I wanted to restrict myself to the original flat space that I had at the very beginning? How would I go from here to here? Well, I'd have to build a bridge to go from here over to here. I would have to have a non-local interaction. So even with this simple example, you can see that if I have a system that lives in a higher dimension, and I now project it into a lower dimensional system, I have to end up with something that looks non-local. Okay, that's what the fractional Laplacian is. It is a non-local operator. Okay, because it requires computing the fractional Laplacian of any function requires information everywhere in space. Okay, so let's take a closer look. For the case that Caffarelli and Silvestri proved, for just a scalar field, we know that this equation gives you, this is what the scalar case of Caffarelli and Silvestri is, this gives you stuff that has fractional derivatives or non-local stuff at the boundary. Now the thing that we're trying to solve is this problem. This is the case that supposedly gives you anomalous dimensions. Well, these two equations are very similar. In fact, the only difference between them is that this is more complicated than a scalar field. A is a one form. So in fact, what one has to do is generalize the Caffarelli-Silvestri extension theorem to p-forms. Well, that's what I did with my math colleague, and here's the paper. It's a fairly long, involved paper, but you can generalize this theorem. So you can analyze what this looks like at the boundary of a spacetime that's asymptotically anti-de Sitter. The result is you end up with a theory at the boundary that has fractional Maxwell equations. So this is the perpendicular component. This is now the Laplacian raised to some arbitrary power. And the corresponding f is not the standard f. It's not dA, but it's d sub gamma, in which now this operator, the fractional Laplacian raised to this power, is multiplied by the exterior differential acting on A. Okay, now note, since this has dimension 2, this is 1/2, this whole thing has dimension gamma. Okay, so there's a new gauge transformation. And the new gauge transformation is A goes to A plus d gamma times lambda. And so this quantity is now the fractional differential. It's not the fractional derivative. So it's because this doesn't change the dimension of the form that it's acting on. Okay, and A now has dimensions gamma. So if you start with these gravity theories that have this dilaton field, the boundary doesn't look like any electricity and magnetism we've ever taught to students. It looks like this kind in which you have a non-trivial gauge transformation. Okay, so now I can answer my question. What is the operator y now that commutes with this? Well, it turns out this commutator is equal to 0. The total differential and the Laplacian always commute. And if they commute, then y hat is just equal to this, and that redefines the current. The current then, associated with a vector potential that has this anomalous dimension, will just have this dimension here. Okay, so you can only understand these theories that have this anomalous dimension, in fact, if they came from one in a higher dimension. Okay, now, is there an experiment that one could perform to test if any of this that I told you is true? I claim there is. Okay, what is the one thing that we know about electricity and magnetism in terms of this formulation, in terms of a vector potential? The vector potential has physical content because if we were to put a tube through a sample and the magnetic field doesn't go anywhere except where this tube is, electrons passing on either side of this tube will know about this because particles are waves, they'll interfere with this flux, and in fact, what you're actually doing is just doing an integral of A dot dl around a closed loop. Now, the reason why A dot dl was always a nice thing to consider is that A has dimension 1. So A dot dl is just a number. It's just pi r squared times b. It's just the flux. Okay? So in fact, one can redo this experiment, or one can think about how would you compute this quantity if A doesn't have dimension 1. A lot would have to change. So if now your gauge transformation looks like this, it turns out the thing relating A to B is no longer del cross A. It's this funky quantity, which means you really don't have a Stokes theorem. And it's Stokes theorem that really allows you to go from this to this with an equality here. Because all you do is write this line integral as a surface integral by taking del cross A. Okay, so the Aharonov-Bohm effect has to change. So what is the new Aharonov-Bohm effect? Well, one can work it out fairly simply. This is some complicated function. It's the hypergeometric function, but the important thing is that it doesn't just depend on the radius, this inner radius. The phase that two current carrying degrees of freedom would in fact acquire is pi r squared b, the old Aharonov-Bohm, times some function of this outer radius and this exponent alpha. Okay, so if this is seen, this would tell you then that the strangeness of the strange metal really is coming about because the current really doesn't have, the gauge field doesn't have dimension 1. Now, is this a large effect? Okay, one can work this out, and the answer is yes. This is 5/3. Remember, it's not a small number. And this effect here is, this is scaling as 1 over the total outer radius. So if you do this experiment for various diameters, the standard Aharonov-Bohm, you shouldn't see any change in the phase. But I'm not telling you there should be a fundamental change in the phase as a function of the outer radius. Okay, now is this experiment feasible? So my proposal then is take, sorry about that, is take a YBCO sample, punch a hole in it, and apparently John Way was thinking about these sorts of experiments in the context of the pseudo gap 10 years ago. So hopefully I can convince him to re-look at this, okay? Punch a hole in the sample, and you're doing this in the strange metal now. So the thing that's relevant in the strange metal are what are the relaxation times? Well, I really don't know, because no one knows. We don't have a theory of the strange metal. But what we do know is that they're probably the worst possible dissipators of all time. So the only way of thinking about that is to say that relaxation time is just h bar over kT. And if it's h bar over kT and you just estimate that for the temperatures which are relevant, you end up with basically relaxation times that are very comparable to what you would see in a metal. And this table is from a reliable book. I happen to be the author of this book. So it's really not so different from what you see in other materials, okay? So I think this is, even though we don't know what the current carrying degrees of freedom are, I think this is a very reasonable experiment to do. And as I said, if this is seen, you will have confirmed that, in fact, this state of matter has a gauge field which doesn't have dimension 1, which has never been seen. Okay? So the strange metal. If you combine all of the transport properties, AC and DC, you can explain them all if, in fact, the current does not have dimension 1. Sorry, the gauge field doesn't have dimension 1, and it's in general some weird fraction. And all of this is implying that the underlying action is non-local. And that's why the phase depends on the outer radius. Because whatever is carrying the charge is now not particle-like. And it's just a bias we have that when we try to interpret the current, we always think there's an underlying particle degree of freedom. In strongly correlated systems, the current doesn't necessarily have an interpretation in terms of particles. Okay. Now, so as I said, this Aharonov-Bohm effect, if this is seen, as far as I can tell, the only way of getting an effect like this is if it's telling you that your underlying theory is actually coming from a higher dimension. So it would be actually a test of extra dimensions. And it wouldn't be coming from CERN, it would be coming from John Way's lab. So I think that's all I have to say.